presenting joint work with Nikki Bazou about adding user-defined effects to Koka.
Sure. All right, thanks. Hello, everyone. So I'm Dan, and Nikki is sitting right there, and she used to be my intern. It was a lot of fun last year. So I'm going to talk today about monadic effects, but unfortunately I don't have any very complex theories, but hopefully it's also going to be like an easy ending of the afternoon. Oh wait, there's one more talk, right? Oh, almost easy. Maybe, I don't know yet, I don't know. An interlude. Let's see how it works out. I should start my little counter here. So let's see. Let's go back from the pure nice world of category theory to the Node.js JavaScript world, where people try to write asynchronous code. And it looks a little bit like this. This looks actually pretty nice. So what you do to write asynchronous code in JavaScript is you have to kind of always give an explicit continuation of what to do next. Right? I think you may all know this, right? So if you do a read line in Node.js, it would be some server request or something, and you say, well, when it's done, then call this function. And then there's the next function coming, you do a little more, and then again you do something like that maybe read from a file or something, and then again you have to give a continuation function. So
you may want to stay close to the mic because they're recording you.
And then again, you pass a continuation function, right? I'll try to stay here. Oh, actually, I think I have. I have no idea. Anyway, but we don't need it. So what I would like to write, and we all know this, like if you're a Haskell programmer, hey, in Haskell you could make a monad and then use do notation to kind of capture the continuation all the time and write a more block structured program. So I would love to write JavaScript like this. So what I really want to do is like take over the semicolon and make it into some monad. And this is what I'm going to talk about today, except not in JavaScript, but in a very nice language called Koka. And I'll get to that too. So suppose I would do this in JavaScript, take over the semicolon. Well, that would be really dangerous, right? Like, so you really want some extra guarantees. And the reason why we feel it's dangerous is these kind of programs, like the program down there. If you're, say, in JavaScript or maybe ML or something, you kind of expect that when you print the I at the end, it should be like 1, right? But if someone can take over the semicolon and put in binds and make it monadic, well, then foo may actually maybe execute its continuation many times, and then you would get many prints, and then I would each time be incremented, for example. And this is the main reason that when in Java, the latest JavaScript, they added iterators, which are a form of taking over the semicolon. And they put in all these, you have to annotate all these functions that do this. And the reason is really that they wanted to prevent people from, using yield inside foo and then doing things you weren't expecting. And what did they do is say, oh, you annotate everywhere, and now you can actually see when it's, what's going on. So really, they made it safe by giving you 12 volts instead of 110, which is like the little kid here. He can safely chew that particular piece of wire. So this is what we're going to do too, but then a much more general way. So I think what you really want is a type system that tells you the semantics, what's going on, such that these kind of programs, you actually know what you're doing. And I think, well, now we can come back to that. So we have a really nice language that I've been developing over the past few years. It's called Koka, and it has a effect type system. So that means that for every function, we also infer the effects. And it turns out we can use this Koka type system as is, and then do a very sophisticated translation to make your own user-defined effects. And I'm going to show that. But before I do that, I need to kind of tell a little bit about what Koka is and how its types look. But I'm going to be quick. So let me see. So Koka is a function-oriented language. I would say it's very functional, but it has side effects too. And some people on the Haskell side are very sensitive about these issues. So function-oriented, where all side effects are explicit in the type. So it is strict evaluation with a JavaScript-like syntax. So in a way, it's very close to ML with a funny syntax, or the other way around. And but in contrast to ML, it infers the possible side effects that every function has. And it's open source, and you can play with it, and please tell me if you enjoy it. So it looks like this. So if I have a function like square that takes an integer and returns an integer, it also shows its possible side effects. So in the first function, there is no side effect. So it's called total. And the arrow really has 3 arguments here. So the arrows have like their input type, their output type, and their side effects. So it doesn't return a total of int. It returns an int and has a side effect, or no side effect. It's total. But when I do some side effecting operation like print, you'll see that the console effect pops up. So and Koka is very strict about this. You cannot cheat. So anytime you do anything that may have an effect, you'll see it.
Am I writing this, or is this?
In Koka, everything's inferred. But sometimes you want to write it to make sure, right, that, is this really total, right? Am I really the function that I'm getting? Must have no side effect, that kind of thing. But it's right, it's all inferred. Very important, because otherwise you'll go crazy. And the way the inference works is because all the effects are based on row polymorphism, and it works really well with unification. So all the effects are really extensible rows of basic effect constants. And sometimes I shorten it with a little comma. So I say, the exception and divergence effect. It's really exception extending a row with divergence extending the empty row. But it's not super important. And then there's polymorphism over effects. So this is very important for your abstraction. So if you want to make so with Koka, I had the goal of making a somewhat realistic language with writing real programs in it. And at that point, you really need polymorphism and abstraction over the effects itself. So there's the map function, for example. It says, well, I take some function from A to B and some side effect E, and give me a list of A's, and I'll return you a list of B's. But when I did that, I may have caused myself effects, namely E, because map will actually invoke the function that's passed to it. So it works out really well, and all because it's using row polymorphism, and that works really well. Let me see actually. So there's a bunch of built-in effects, but very few. The rest is all user-definable, but divergence and exceptions are built in because the compiler needs to know a little bit about that. So here you see a square function that may diverge. Actually, it probably will many times. And then you can also see it's really a type system, right? It doesn't know anything about actual control flow. It always takes a conservative approximation. And yeah, in contrast to, say, Haskell, total means really mathematically total functions, and pure means it may raise exceptions or diverge, right? Which is not too bad, actually. That many programs are in that class, and it works quite well. So one thing that's really important. Oh, can I?
Yeah. Are the effects ordered here? Is exn comma div the same as div comma exn?
Yes, they are the same. Right. So they're unordered, and there is some subtlety there, but I won't get into it during this talk. So about the duplicate labels, right? But yes, so they're unordered. So just you could see it as sets of effects, but it almost.
There weren't any row types. There's not a row type in the pure is there?
Well, so the row type, this is like it's a type alias.
Sorry, there's not a row variable.
Here there's no row variable, right?
So what happens if I try to use a pure function in a different effect context? Say I annotate my function to say
right.
I try to run it.
Yes, so you can right. So when you use a function, it's like implicitly extended with an open tail. So you can always, you can use a pure function together with a say a non-deterministic function, and then their effects will be combined in a bigger row. So you can always use something that has less effects in context where more side effects are happening, and it will work out. But I'll take that offline because really, besides the talk now, right? So, but what's important for me with Koka was that the effect system is not just little labels that I attach to the types and that I figure out like what's going on, but I wanted to have it really strongly related to the semantics. So Koka can really not cheat, right? If it says total, it's really total, and if it says I only have an exception effect, then it should only have an exception effect. And the idea is really that if you look at the type of a function, you can kind of translate it to the type of a mathematical function that would model this program. It's denotational semantics. And then you can kind of see that what I'm doing here is like a monadic translation, right? Where I'm showing that. And I always thought, great, I'm going to do a monadic translation with beautiful category theory. But it turned out really hard. So this is why I was so excited by the talk this morning. Because it's really hard. And in the end, I wrote a paper where I kind of gave up and did operational semantics instead. But it's worked out fine. It's like good standard techniques. But it doesn't give you a feeling of why, right? And I think so. I was very excited about that talk. So maybe one day. But this is the intuition.
So what will it give you apart from a fuzzy feeling without the visual semantics?
What's that again?
What will it give you apart from a fuzzy feeling to have it in visual semantics?
Why I get that?
Yeah, what?
Because this is beautiful. Like like operate now. Like things like so when I did the proofs for Koka, so it has lots of side effects. And then here you see the statefulness thing, and you see divergence. And we all know that if you have statefulness and you can write functions that are not recursive and still may diverge, for example. So why is that, right? What is the real point where that can happen? And what should you do in your type system to prevent issues with like the value restriction or let polymorphism that's unsound? All these issues come back in Koka. And in the operational semantics, I can kind of prove that the bad situations don't happen because of the type system, somehow, but it doesn't give you a deep intuition of why this is all working the way it is. And that was what you were saying too. So it's in that sense unsatisfying. And I think a good categorical treatment would make it really clear. I made some progress there. But anyway, I need to really go much faster. Oh my God, 12 minutes. We're getting now to the interesting part. So I want to do my asynchronous monad programming in JavaScript, but first we do it in Koka, and we do it much simpler. I'm going to do just the ambiguity effect and it's really the list monad, right? So the idea is that we have some operation called flip, and it says, call me, I'll give you a boolean, but I'm ambiguous. And then I get from amp, and it says, well, give me some computation that has an ambiguous effect, and I'll give you all its possible answers. So flip will really do both true and false, and then you can maybe later get a histogram or something of all results possible. And a program would look like this. So you use your monad that we're gonna define as an effect, right? So here I write XOR by saying, oh, I flip twice and I get a P and a Q, and then I do some logic stuff that's supposed to be XOR. I never actually checked that. I just trusted my intern Nikki to do that right, but I think it's XOR. And then I'm gonna print it out, and then when I print it out, you should really get a list of all possible answers, of all possible results that flip could give, right? So let's try it. I actually prepared a little program here. There we go. Here's like a little program. You can see it's really there. This is Koka. And then I have a little console here. Let's see if I can start Koka. There we go. Okay. And then I'm going to load. Okay. And then I'm going to run it. wow, great. False, true, true, false. Can everybody read that? Maybe I should. Can you read it? Or? Oh, okay, then I'll just leave it. Maybe I can. No. Okay. So it worked. Somehow it gave a list of all possible results, even though I just wrote one XOR function and I only called it once, right? But from amp will do its magic. And yeah, so that really works. So and how does it work, right? Because I just have here some side effect, but somehow I called XOR many times, and basically without knowing how many times to kind of get all the possible results, right? So the answer, of course, is we defined amp as a list monad. So we use here as an effect, we do our programming, but when you as a library writer write it, you define it as a monad. So you can have these effect declarations where you say, well, I'm going to define a new effect, amp, over some type A, and it's going to be implemented as a list monad, as a list data type of A's, and you give a unit and bind operation, and then it brings into scope these operations, right? So it gives you a new effect, and it gives you a reify and reflect operation, a la Florinsky. So it's called to amp and from amp, because reflect and reify, I can never figure out which one is which. So to amp, takes a list of things and makes it suddenly so it takes a list and it has an amp effect, but just gives one A. So there you can kind of see it happening, right? And the from amp says, well, give me some computation with an amp effect, and I'll give you back the list of possible outcomes. Hey, and that, like, look, if you look in my original, my example program, you'll see it's right there, right? Like, there's the unit, there's the bind. Oh, I already showing you flip. I shouldn't do that. That's actually my. And you can define flip like this, right? So you can do with to amp. You say, oh, I will be returning first false, and then I will be returning true. And this is all. I think this is very different than when I showed you the dangerous slide, because here your effect always tells you what's going on. Right? You're very aware that we're now programming with some amp monad, and that certain expressions, like this expression, may be executed many times. Now you're aware as a programmer what's going on, and it's no longer some implicit operation that can happen. Okay. And the way we can all implement this is there's many ways, but one way to do it is to have a type-directed translation. And it turns out that if you take the Koka intermediate representation, it's strongly typed, you can actually do all of this as a separate phase after type checking, which is a big advantage in practice. Oh, I got still off. Okay. So here are the formal rules. So I'm following Simon PJ's advice of not showing you formal rules, but you can read the paper to figure it out. Or actually technical report. I don't think I submitted a full paper, but maybe later. But here's how it works, right? So the whole XOR function that we just saw gets translated into a whole bunch of binds, where you now see that the compiler inserts all these continuation functions for you, which is really what we want to do. You also see how the type changes from first being a function with a possible effect amp and returning a boolean to a total function returning a list of booleans. And that's kind of nice. So we do a translation inside Koka intermediate language to Koka again, but now without any of these monadic effects. So I can use the standard semantics that's been proved sound for this too, because it's almost it's a Koka to Koka core transformation. And a nice thing is that the reflection operations become identities, like they don't do anything. Because if you think about it, you see the first type, like to amp, list of A, amp effect to A. When it gets translated, its types become list of A to list of A. Like it doesn't do anything. And it's the same with the from amp one. So they're both identity functions. So that's nice. They're very cheap to use. So it gets a little tricky with polymorphism over effects. So here we see the map function we saw earlier, and it's polymorphic in E in the effect. And I switched the arguments too. And we would like to use it unchanged for monadic effects too, and that just works. So you can define the XOR function as mapping over some list, and then do flip for every element in the list, and then use those P and Q, and it works just fine. So the abstractions keep working even for your monadic effects. And that all works because we have to pass evidence at runtime now, because we have to, when we have a map function, it doesn't know how to bind your particular monadic effect. So the translation for those functions becomes quite a bit more complicated, because here we see the map function and it says, like, well, but if you give me some function that itself becomes monadic, that will have a user-defined effect, we have to pass in an extra argument, a dictionary, that gives me the unit and bind functions, and call the unit and bind functions at the right points for the function you're going to call. And this is very similar to Haskell predicates that are passed around, dictionaries that are passed around. And then, when the XOR function here with the map in there is translated, you can see that the compiler will pass the dictionary for amp as an argument to map, where it becomes concrete. Clearly, the translated function of map is not so efficient compared to the one that's like plain, because our backend is usually something like JavaScript or C#. And so we generate, for all these polymorphic functions, we actually generate two versions. One that's translated with monadic support and takes a dictionary argument, and one that's used if there's no user-defined effects going on. And that was a little tricky. I was always worried that, oh my god, it will like explode like crazy, but it's not too bad. It's like for the standard library, which has many of these polymorphic functions, it's about 20% increase. So I think that's worth it. There's one really important constraint in this whole work, and it's kind of done to simplify both implementation and the formal treatment. And that is that I didn't want to introduce a new type language with new constraints. So what we said is, well, we're going to pass at most one dictionary, and we're only going to pass it where an effect is abstracted. So here you see there's really a big lambda E for all E right there, and that's where a dictionary comes in. And we never allow more than one to go in. But that gives trouble. Like sometimes you'll have functions like this. So I have some function foo. It doesn't happen often, so I couldn't come up with like a great like example that everybody could get. But I'll just give like the idea. It takes a function amp with some E effect, but now you see in contrast to map, it says, oh, myself, I also did something ambiguous. Like so, I also have an amp effect in addition to whatever F may have as an effect. And now it gets troublesome, because if someone passes in an F that has, say, a behavior effect, then how do I bind behavior with an amp and behavior? And how do I lift the amps to amp plus behavior? Like how I combine all of these. So in that case, you would have to pass three things, like dictionaries for the entire combined monad and all the morphisms for each one separately. And that's much more tricky, so I thought, let's just not do that. So we'll just say, no, you can actually write these functions, but when you try to use them in the way I just described, it will be rejected. So I will, like the compiler checks that you cannot instantiate polymorphic type variables which would lead to a combination of that sort. So in practice, that doesn't seem to be a big problem yet. But it's really because we didn't do much automatic combining of of monads. And that's something like when you think about it in Haskell, you can't do that either, right? There's always you have one monad, and if you want to combine two monads, you have to explicitly lift yourself. So you can always like work around it, but maybe it's an area for future research. Effect handlers, right? So they handle this kind of situation in right, yeah.
You could also pass the morphisms.
Yeah,
Ouch.
there,
It's the mention.
I have so little time. I want to show, right, I only have very little time. So let me skip the parser. You can make parsers, of course, you can make parsers. But I want to do the async, the JavaScript one, right? So this is how you write it in JavaScript. So you can write it like this in Koka. Okay. Do you want me to demonstrate now? Believe me, it works. No, let's actually demonstrate. Why not? Right. So let's do async. So I have an async program. There it is. Right. It's really there. It's like print line. There's the game. You know, everything's there. And there's an async effect. And then when I run it, I think I called it done. 24. Great, my age is 24. It worked, right? You saw like a little wait and everything. And this is a fully asynchronous program using fully asynchronous JavaScript primitives for read line and console I/O, which is pretty cool. And the way it's implemented is to a almost standard like asynchronous monad, which really takes two continuations, one for success and one error continuation. And like continuations always have these crazy types. So I will not explain it, but if you're into asynchronous monad programming, so you will probably see that this is kind of what you normally do. I have to do very special take care of exceptions, and it really has to do that I'm interfacing with an underlying JavaScript engine, which is really outside my semantic domain, because it does the outer event loop that calls the continuations completely outside the language. So.
It looks like async, in that case it's like an async transformer for the underlying monad, right? Because when you compose async and I/O, those are two monads.
Right?
And generally they don't compose, except if async is async T, which is a transformer.
Right.
Is there an analogy here?
No, unfortunately not, no. Because it's really the interactions with the built-in effects. And you could see the analogy is that the built-in effects are always, on top. And then your user-defined monads are like underneath it, because you cannot kind of get out of your built-in effects. So it would really be I/O of async. But async is a tricky case because it's so dependent on the outer mechanisms. Hey, and so it turns out you can all define this in Koka itself and interface with these continuations. And if there's any questions, I would love to hear it.
We have time for questions while Ralph sets up.
Great.
I was a little confused by so you mentioned at the beginning you were worried about changing the semicolon. Maybe I misunderstood.
Oh, right. So what I mean by that